Okay. So, we will start solving our first example problem related to Euler's laws of motion. We looked at the application of the Euler's laws, where the rotational motion was essentially a static equilibrium. That was the previous block sliding problem. We are going to look at a case where the rotational motion is non-trivial, that is, it is not simply a static equilibrium, and this is, let us look at the problem. There is an inextensible cable on which we have a cylinder of weight 64 newtons, and this cylinder is going to be rolling down. We are asked to find the acceleration of the mass center of the circular cylinder as well as the tension in this cable. So, we are going to assume the cable is massless. Okay, so, let us start doing the problem. The first thing to do is to make sure we learn how to draw free body diagrams. So, I am going to draw the free body diagram of the cylinder, and the idea of a free body diagram, like we said, is to replace the effect of all other bodies by forces. So, the cable is now removed. The cable exerts a force T, which is the tension in the cable in a downward, in an upward sense, and the gravitational pull is also being removed, and that results in a 64 Newton force acting through the mass center. These are the only two forces acting on the body. So, let us say the acceleration of the mass center is A and the angular acceleration is alpha. So, the first thing we are going to do is apply the laws of kinematics, which relates the angular motion to the linear motion. So, if you think of it, at this point A, where the cable comes together, where this cable comes in contact with the cylinder, if the cylinder unwound a distance, an angular distance theta, the point G would come down a distance r times theta in a linear sense. So, this problem is akin to a cylinder rolling down an inclined plane under no slip conditions. So, what we end up finding is that A equals r times alpha. So, the linear acceleration of the mass center and the angular acceleration of the cylinder are related. So, this implies A equal to half times alpha. The radius of the cylinder is half a meter. So, now applying the laws of kinetics, the first law, first Euler's law says I am going to take downward motion positive, sum of all forces is mass times acceleration, which means 64 minus T equals 64 divided by 10 times A, or 64 minus T equals 6.4 A. So, this is our, I am going to mark these equations. That is our first equation, this is our second equation, and the third equation comes from applying the laws of the Euler's second law about the center of mass. The moments of all the forces in the system taken about the mass center is equal to the moment of inertia of the body times the angular acceleration. Now, I do need to compute this Ig. Now, this is a regular body, it is a cylinder. So, I can, there is a known formula that the moment of inertia of a cylinder about its mass center is half times mr squared. So, that is half times 64 divided by 10, the mass of the cylinder is 64 divided by 10 times the radius is half a meter squared. So, Ig we find out is 0.8 kilogram meter squared. So, taking clockwise moments positive. Now, this sign convention that we choose is this has to be the same as the sign convention that we chose for alpha. That is because if you do that, you only have to worry about the signs of the terms on the left hand side, the moments. The right hand side, Ig times alpha, would always be positive. So, that eliminates one little thing to worry about. Now, the tension in the cable has a moment arm of half a meter. The weight of the body does not have a moment arm. This equals Ig, which is 0.8, times alpha. So, simplifying this, I get T equals 1.6 alpha. This is my equation 3. So, let us recap. I have 3 equations. In 3 unknowns. I will be slightly more precise. There are 3 linear equations in 3 unknowns. The 3 unknowns are T, A and alpha. So, I will just for the sake of completeness, I will do this once, but we are anticipated to know how to solve these for the next time. These are the 3 equations, 64 minus T, so I will substitute 1 into 2. When I do that, I find out 64 minus T equals 6.4 into half alpha, which implies 64 minus T equals 3.2 alpha. Now, substituting, I call this equation 4, substituting 3 into 4, alpha is 13.33 radians per second squared. The linear acceleration is half of this, which is 6.67 meters per second squared. And the tension is 21.33 newtons. Okay, so a couple of quick checks. Alpha is positive, so there is no surprise there, because intuitively you would find a cylinder such as this would roll down. So, alpha is 13.3 radians per second squared. You would find intuitively that the cylinder would have to roll clockwise. And a second check is that if the system was in static equilibrium, I mean, which is not possible with the configuration shown here, but you can see that the tension in the cable should only be less than 64 newtons. In fact, the tension in the cable is only needed to enforce no slip at this point A. That is, you need a moment which cannot be created by the weight of the cylinder itself to cause the cylinder to roll. So, this is the role of the tension in the cable. The tension in the cable is essentially causing the cylinder to roll to roll with no slip at the point A. While the weight of the cylinder is trying to accelerate the cylinder in a downward sense, the purpose of the tension is to add whatever rotational motion is needed at that point. Okay. I hope this point illustrated, I hope this problem illustrated the use of both laws of motion in a dynamical way in a simple one body system. Now, I do want to reiterate this once more, that the Euler's laws of motion, which say sum of masses is mass times acceleration, sum of moments about the center of mass is the center of moment of inertia about the center of mass times the angular acceleration. This point is very important. If we do not, for example, in this problem, if we did not take moments about G, but we chose to take moments about another point, let us say A on the cylinder, we would actually get an incorrect answer, because the point A has a linear acceleration, may have a linear acceleration, and which may lead to incorrect results. So, we will continue our discussion with another example problem later on.